Future of Analytics, a Roadmap. This is an in-depth presentation on the future evolution of what is often called analytics or machine learning or data science by Dr. P.G. Madhavan. P.G. is the Chief Analytics Officer of Syzen Analytics located in Seattle. Here is P.G.
Thank you for tuning in. I'm delighted to share my unified view of current analytics or machine learning and glimpses of the future of analytics that I've been privileged to see. This talk is not a tutorial nor an introduction to ML. If you have already watched an ML online course such as Andrew Ng of Stanford University's Coursera course, you will get more out of my talk. Conversely, once you listen to my talk, ML online courses will make more sense, since you will see how various algorithms fit into the big picture rather than see each of them as shiny new objects. At the outset, let me say that I'm firmly in the camp of intelligence augmentation, or IA, and not AI, which is artificial intelligence. As a card-carrying neuroscientist, I can say that creating artificial intelligence by mimicking the human brain seems to be a fool's errand. If you think about neuronal axons along which electrical spikes travel, they are like conducting wires with insulation scraped off every few millimeters. Then the whole jumble of these billions of wires are dunked in a salt solution. Try sending your TCP/IP packets along such a network. I believe that the electrical fields that these leaky wires produce have a major role to play in how the human brain works. Our current silicon models, or software models for that matter, have no way of mimicking these electrical fields. In fact, they are actively suppressed by proper layout and ground planes everywhere in hardware. Now, there is a glimmer of hope for artificial intelligence. Our ancestors saw flying birds and dreamt of flying. But our planes don't flap their wings, and they fly really, really well. Similarly, there may be a Wright brothers who finds that last twist in the story and creates artificial intelligence that works like human brain, but not by flapping wings. Coming to intelligence augmentation, when Doug Engelbart wrote to ARPA about IA, intelligence augmentation, in the 60s, he could not have foreseen what big data can do. Engelbart's mother of all demos was really about communication augmentation, computer mouse, video conferencing, hypertext, etc. With big data and analytics, now we can truly do intelligence augmentation. This is why all of us ought to be excited to be working in this field. Here is a glimpse of our roadmap. We enter the technical domain of theories, system theory, state spaces, random fields, etc. This will lead us gently to systems analytics. What is it, and what does the roadmap say? To start with, analytics or machine learning? My answer is both, plus the following: pattern recognition, statistical modeling, predictive analytics, data science, adaptive systems, self-organizing systems, and more. We won't worry too much about nuanced meanings. There are differences, but not in our present context. Data science may be a bigger umbrella term that one could use. One more definition before we go. Big data. To me, it is not peta or zettabytes. If you have measured the entire population or close to it, and not just sample a small fraction, resulting data is big data. You know what analytics or ML is. No need to define them here. Both have to do with learning. That is, the ability to generalize from experience. A necessary feature of learning is feedback, either explicit in the case of supervised learning or implicit in the cases of unsupervised or reinforcement learning. In the latter cases, there is feedback in terms of some larger good of the system. There are a class of algorithms that are very useful but do not exhibit the learning and feedback behaviors. We will exclude them from our current discussion of analytics or ML. Note that algorithms such as decision trees are more of machine discovery, so it's like data mining rather than ML. Such panning for gold is very useful but does not involve learning or feedback about the gold itself. Let's take a close look at analytics ML algorithms that utilize learning with in-band feedback, or I call it LIF, learning with in-band feedback, in a unified manner. Let's call them LIF ML for short. We will select a business context to explore LIF ML for the rest of this chat. Now, I'm a businessman who is interested in producing practical solutions to vexing problems. I happen to know a few other topics, but don't let me hide behind parametric equations of n-dimensional manifolds or state space volumes of n-dimensional probability density functions, etc. Call me out. I should be able to explain any concept to a smart lay person. So, we won't split hairs about definitions, be happy with 80-20 solutions, and in general will seek optimal rather than perfect solution. So a takeaway is we look for pragmatic and optimal solutions. Another reality to keep in mind: there is hardly ever a business solution that is one and done. What do I mean by that? One-shot solution will forever solve the problem. Like lifelong immunity from, say, chickenpox. By the way, even that is not perfect. Shingles can show up later in life. But almost all business problems I have seen are more like needing yearly flu shots. Monitor the outcome of the first solution, tweak the mix, administer again after a while, and so on. As data scientists, we have a duty to educate business clients to subscribe to this view, what I call goal-seeking or tracking solution concept. The first solution may be just 80-20, but track and improve over time. With such realistic expectations, your customer will be delighted if the trajectory is good and fast. For a data science company, this is good. Recurring revenue. Clearly a win-win situation. So keep collecting data over time. So the big takeaway here, always talk about goal-seeking and tracking solutions. With this preamble, let us define a canonical or prototypical business problem that will help crystallize our unified ML approach and the analytics roadmap ahead of us. We will consider a retail commerce business domain problem, brick and mortar grocery store chain, and CPGs, consumer product goods manufacturers, who supply them with fast-moving consumer goods. It's called FMCG. Before we go further, you may ask, why not e-commerce? Very simple answer. Look at 2014 data for US. Total in-store retail, $4 trillion. E-commerce, $300 billion, or 6.4%. I want to address the much bigger business opportunity. And e-commerce is leveling off, and projected e-commerce plus m-commerce total in 2018 is expected to be around 11%. So stabilizing. But more importantly, by then, omni-channel movement will make the distinction among in-store, e-commerce, m-commerce irrelevant. Sales attribution to any single entity will not make sense anymore. So consider a grocery chain with 100 stores, say. Assume that each store has 5 departments, 20 product categories per department, 50 brands per category, and say 70 SKUs per brand. Product category is the level in product hierarchy to focus, since shopper choices are within a category. You choose between various brands of yogurt, but not between yogurt, which is one product category, and soap, which is another product category. So each store has 100 categories, 1,000 brands, and 70,000 SKUs. This is called the product hierarchy. So here is your neighborhood and stores in the vicinity. This is my favorite town, Takamatsu, on the inland sea in Japan. You can see 4 7-Eleven stores, but in fact there would be 3 in practically each street corner. That is a lot more than what you see here. And I've kind of indicated that activities near each store are dramatically different. One is near a school, one is near an office tower, etc. How does the store manager at one of these stores decide what products to carry? This is called the optimal product assortment problem in retail merchandising. This is important not only to the retailer but also to the CPG that supply products to the store. Now, the store manager can make 1. Educated guesses, but not very reliable. 2. Ask shoppers what they want, but this does not scale nicely. And number 3, rely on market survey data, but it's usually based on sampling. It's not usually specific to at the SKU and store level. Using big data and analytics, can we do better? Let's explore a basic ML solution for the problem. Recommendation engines are commonplace today. Who has not heard of Amazon or Netflix? They provide recommendations to individual shoppers for goods or movies, based on a particular shopper's likes and dislikes, as well as sellers' business priorities. They push out more movies in the long tail for Netflix and sell goods from the fat front from Amazon warehouses. Optimal product assortment is a slightly more difficult problem. We need a recommendation engine for a group of shoppers, one for each store. Note that the optimization problem arises because shelf space is limited. By the way, this constraint applies equally to large e-commerce warehouses, where the shelves are numerous, but the products to stock are even more. The challenge is actually product density. The natural approach to such a problem is to group the hundreds or thousands of shoppers at a store via segmentation or clustering. Once grouped into these few segments, the recommendation engine can be optimized for each segment, and the optimum product assortment can be derived from the proportion of these few segments that shop at that store. The state of the art in commerce is behavioral segmentation, where the market is divided into segments based on pre-selected characteristics which applies to all product categories in a store. Clearly, bucketizing shoppers into convenient segments such as price sensitive or families allows one level of meaningful abstraction. Instead of addressing millions of shoppers individually, one can tailor marketing, merchandising, and loyalty efforts to a handful of labeled groups. In traditional behavioral segmentation, we would have predicted that brand X will sell more in store 123 because price-sensitive shoppers prefer more of brand X, and the store 123 has more price-sensitive shoppers. Now let's consider a better approach using shopper big data and machine learning to create and identify the segments. In ML segmentation, the shoppers, whatever their behavioral characteristics may be, fall into N preference group 3 shown here, based on what they actually buy. By the way, actual purchase pattern is a great proxy for true product preference. In essence, each product category is its own unique market. We have compared our behavioral segmentation and ML method to optimize product assortment in a head-to-head test, and we obtained the following results. Improvement due to our data-driven method is 5 times higher than that due to behavioral segmentation. So the key question is, why is ML method better than behavioral segmentation? The table on the left-hand side captures the reasons. Looking at more dimensions than just the head-to-head comparison result, it is clear that ML method has several advantages when it comes to merchandising. Whenever the data itself determines groups rather than being externally imposed, data analysis history has shown that results will be superior. Another nice feature is that the human labor and the subjectivity in bucketizing can be avoided, which makes analysis fast, inexpensive, and most importantly, repeatable. The fact that separate preference groups are generated for every product category and that the ML method acts on what people purchase rather than why, has led to breakout applications of this ML method in retail merchandising product assortment optimization. In developing a group recommendation engine, you would have noticed that we have added an aspect of modeling to the solution. This word modeling is going to be very important. We modeled the shoppers into n preference groups. Another way to look at it, it can be said that any shopper can be approximated as a weighted linear combination of these n groups. Let us keep this perspective in mind for systems analytics, which explicitly uses model-based thinking and algorithms. Coming to systems analytics. Remember the takeaway from an earlier section, goal seeking and tracking solutions? This is the context of systems analytics. The product assortment optimization problem and solution can be reformulated as shown, keeping in mind that we have to track the solution over time. In the retail case, shopper preferences change, product attributes change, local population around a store changes, some quickly and some slowly over time. We want to adapt to the changing circumstances and provide frequent updates of product assortment solution to the store manager. A complete characterization of the retail dynamics is captured in this canonical diagram shown on the left for the demand chain side. Retail business is about increasing customer acquisition and retention. Then all good business things happen. Business owners have three levers to affect change: marketing, loyalty, and merchandising. Our prototypical business problem laid out earlier was retail merchandising, so we'll focus on that loop. For the basic solution, instead of behavioral segmentation, we used ML to discover n preference groups, or what we think of as models, to create a group recommendation engine for each store. What's shown on the right-hand side is a specific instance of such a solution from Syzen Analytics, where they use an ML algorithm called progeometry for preference group, which uses unsupervised learning, and create optimal product assortments for each store, that is the SKU shares output. The overall group recommendation engine for each store generates feedback information, here labeled as ROG, for supervised learning, which tracks optimal product assortments over many quarters. From this example, we can formalize ML within the systems theory context, and that's what we call systems analytics. Notice that the following is the essential structure of an ML system. Traditional machine learning system components are shown in the middle. This must be familiar to you from your previous exposure to machine learning. And you also know that the business of this system is to learn the true target function f and approximate it with a function g. There are many well-known models, structures, and learning algorithms, some of which are shown in the table, the first three rows. We are adding a new row, the fourth row, called systems analytics. So the model is systems, structure is state space, learning algorithm is Kalman filter, but the objective remains the same as the traditional machine learning algorithms. The state space model and Kalman filter algorithm define the basic systems analytics framework. There are many simplifications possible, of course. For example, Markov model is a special case of state space model, typically used when there is a context-sensitive information in the input, such as recognizing a word within a sentence. Instead of Kalman filter, there are other linear algorithms, such as least mean square, or nonlinear ones, such as extended Kalman filter, which is used in every GPS device that you carry. The power of systems analytics formulation is that many other models and algorithms that are well developed in system theory, control theory, process control, system identification, and stochastic process, among many others, can be brought to bear on ML problems and perhaps lead to powerful solutions that have formal basis in mathematics and thus go beyond ad hoc and heuristic approaches. We have brought systems analytics into the well-known machine learning framework to show their equivalence. From this brief discussion of a systems analytics business example, the following must be clear. We have a framework for a closed-loop analytics solution. We also have a framework for real-time analytics, goal-seeking solution that improves and delivers results over time. In this case, the time period may be weeks, days, or milliseconds, depending on the application. Network dynamics. Earlier we considered individual shoppers' purchase propensities, which we aggregated appropriately to find product assortments. As businesses push to higher levels of performance, higher fidelity models are going to be needed to produce valuable predictions and recommendations for business operations. In the case of a shopper, she is not an isolated entity, but influenced by her social and influence networks. In other words, data exists in embedded forms in preference and influence networks, which are distributed in time and space. In this sequence of pictures, starting from the left, we recognize the following. Shopper can be considered isolated for early models, but truly exists in a social network. In current network graph theory, it is often the case that the space and time dimensions are ignored. In other words, influences happen instantaneously, a bit like spooky action at a distance. With global connectivity, shopper is influenced by events around the globe. Bringing such practical considerations into a mathematical framework is devilishly difficult. There are some tools and techniques. For example, our work in spatial frequency distributions, which estimate spatial frequency at a point in space, may be applicable to some cases. This is an area for future development. In general, engineers like to reduce the parameters of interest to a few scalars. In a typical Internet of Things or IoT application, we may track the variation of a scalar over time, put thresholds or bands around it. When exceeded, raise an alarm to alert a human or take some automatic corrective action. Such measures as spatial frequency distributions simply do not lend themselves to such an approach. In fact, considering only the spatial extent is a gross simplification of the real situation. Data is changing over space and time. The following picture captures the true complexity. As you see, the data is flowing in waves across space as well as it is changing in time. So the shopper shown in here in yellow is being influenced by all of this over time, and the spatial effect has to be considered. Instead of attacking the spatio-temporal data analysis problem head-on, I think it is time to take a different approach, because this is very complex. So let's see what's underneath the surface activity. We hypothesize that the surface activity is generated by a few real or virtual sources, and the coupling among them creates a spatial temporal dynamics that the surface data showed in the previous slide. This has a long history. In the case of earthquake and scalp EEG studies, one can find many articles that develop dipole models that hypothesize deep virtual sources that oscillate, producing the data recorded on the surface. Then the data description problem resolves to estimating parameters of the dipole models, a much more tractable problem. Once these source model parameters are estimated, they can then be used as high-level features for the type of problems we discussed in retail. For example, if you think these global pictures as showing the preference for a product, or the dynamics of a tweet, or the effects of a marketing campaign, we start to realize that for certain levels of business analysis, the surface data themselves may not be as relevant as the coupling among the sources. Your business may be interested in manipulating the couplings such that the desired surface activity is produced over space and time. Let us see how that can be approached. We talked about coupling and spatiotemporal dynamics. Spatial temporal dynamics and surface activity can be thought of as a random field. In the 80s, Eric Van Mark developed a new fundamental formulation of the theory of random fields. Subsequent work has extended it to systems applications and estimation, where I have played a part. An important parameter in Van Mark's formulation is called scale of fluctuation, or theta. Theta turns out to be a mini-splendored thing with some amazing properties. There is an accessible discussion in my blog, Network Dynamics and Coupling, Shannon Reverie Reprised, shown at the bottom left. There I develop Shannon entropy with minimum probability theory, and in a similar fashion develop scale of fluctuation also. It may be worth spending some time reading that blog. Now on the right hand side, show A, B, and D are still open problems in random field theory applications. I'll be happy to discuss it with you at a later time. Relevant to our current discussion on source coupling, the diagram of interest is C. Theta is on the x-axis. What the figure shows is that as theta increases, coupling strength increases. On the surface, its effects will be seen as a nearly uniform color in the global map. This is akin to a slow swell of a wave spreading across the world in a very orderly fashion. On the other hand, small theta indicates a chaotic wave pattern with local disturbances over the surface. As you can tell, the explanations above are very suggestive of some of the aspects of a global marketing campaign, which can be tracked by a single scalar. We always love that. Now, theta has much deeper and more complex interpretations than as a coupling measure, which may also be valuable in analytics applications in the future. Now let us pull all the things that we have talked about together into one diagram. For those with ML background, many of the blocks are familiar. Supervised learning, unsupervised learning, linear discriminant functions. So within this diagram, without going into great detail, I'll point out that the topics we have talked about, things such as state space, systems analytics, scale of fluctuation, are fully integrated into various blocks. So these are alternatives to the ML techniques that you already know and can be incorporated. And once the patterns have been recognized and classes identified, the resulting classes can be used for all sorts of applications, such as recommendation engines, for language translation, for fraud detection, and many, many others. This is the roadmap that we have discussed so far. We have sketched out a roadmap of increasingly complex tools that can be brought to bear on analytics or machine learning of today. These tools provide us with high-value features in terms of system parameters and a framework for closed-loop real-time analytics and ways to possibly accommodate the network nature of data sources. Theories of all the techniques introduced are fully or partially developed, but will require thoughtful additional development to reach their full potential for analytics applications in the coming years. I've been privileged in being involved in the development of the basic theory of each of the topics discussed. I've also personally developed the base algorithms for each case. Breakthrough business applications of the later milestones will require significantly more development in collaboration with business domain experts. I look forward to our collaborative journey along this road. Thank you.
For a full article on the same topic, Future of Analytics, a Definitive Roadmap, please go to the link shown.